Swayam Prabha. Digital India. Educated India.
Next topic is innovation, which is I'm very proud of, and most of my projects with industries are now with this, because when I get a contact in an industry and I say a few things, immediately they say, can you list down all the things you are doing in your lab and let us see how we can collaborate with you. Okay, so that's kind of sometimes a question I get. So I have a standard file where I have bullets and I do these things. Most companies pick this one up. They said, this is what we want to do. So what is it? It's basically innovation through optimization. So I kind of did a crossover of these two words. It's called innovation. I coined this word way back in 2006. It has caught on to some industries who know about it, so it's a second step after multi-objective optimization, as we will see soon. So what is it? So let's say I have a single objective optimization with one objective function. Okay, one objective function, and then I have a design space where any point here is okay for me if they are feasible, and then I want to know the objective function. So after we do the optimization, I find the minimum, and then I can look at the minimum solution. Okay, it's just one solution. And if that's all you have for your problem, what can you learn from it? Yeah, you can appreciate the solution saying, we have some small size gear here, there is a big one here, the helix angle, all these you can see and say, okay, fine, it must be good. That's why I'm seeing all my objectives and constraint good. There is not much you can learn from one solution, right? But what if we did a multi-objective optimization? Now you are going to have a Pareto set, right? You have more than one solutions. Now you can compare one solution with the other and things like that. I'll come back to this slide. But let us say that I have done this on a electric motor design problem, actually at some point with my student, and we got a thesis from Stanford University where they given all the form. The whole thesis is about formulating an optimization problem for this brushless DC permanent motor design. There are about 50 different parameters it has for design. Okay, and we said we are showing some feature of that innovation aspect. We don't need so many. We fix many of them, actually just 5 of these variables. Here there are 4, but then was there 4 or 5? I forgot, 4 I think. 4 variables we just kept as variables, all others we fixed to some value. And then we did a multi-objective optimization where we want to maximize the peak torque and then minimize the cost. Okay, so we get a nice trade-off front, and there are about 100 different motors that we've got here with the very small cost but not much torque it can deliver. This one is high cost but it can deliver a lot of torque, and that's the trade-off we get. Now I am interested in what if I go from this to this to this to this to this, what is changing? Because I have 4 variables for each, all other 45 of them are fixed, right? So they are not going to change. These 4 can change, and I am interested in seeing what is changing. As a designer or an engineer, do you think everything will change randomly when I go from, because there is no relationship, right? Apparently, each one of them is an independent Pareto solutions. Why would there be any relationships among the variables? The reason is this one here. So we have objective function and constraints that follow some engineering principles, applied mechanics, Navier-Stokes equation, whatever, at the background of coming up with the objective function and constraints, right? They should show up somehow. And in addition, all these solutions that are on the Pareto optimal front are optimal. And remember, I showed you the Fritz-John necessary condition that every Pareto solution has to satisfy. So these are these conditions. Somehow these conditions should show up in my Pareto solutions, that these are invariant along that. So that's the reason I expect there will be some relationships. What kind of relationships? If I call this x1, x2, x3, x4, maybe some of them are constant. x1 is constant, or maybe x2 and x3 are correlated. Let's say if x2 is double of x3, not in this problem, but in another problem. Because if you do that, then only you stay here. Otherwise, you are here. So which means I have now found some signature properties of the variables of Pareto optimal solutions. Those signatures will say if you meet them, you are on the Pareto set. And there are some other things you have to do differently so that you go from one Pareto point to another Pareto point. So that's the idea. I hit up on this idea while I was dealing with some industry problems. I found that these variables are lining up in some way. My initial thought was it's something wrong in my code, and that's what's causing it. But then I thought further and realized it is expected that they will have some relationships, and it's so important these rules are. As I said, most industries pick this topic because in addition to finding optimal solutions, they are also interested in knowing or learning something about the problem. So here it tells you a lot. I'll show you some examples. Here is the first one. So after I did that, and so all this is done manually, but today we have machine learning methods where these points are input to the machine learning code, output are all these principles and rules that we come up with. So here we did manually, and we observed all of them have the Y connection. The way, in electrical engineering, you can have a Y, the three wires can be connected in a Y form or a delta form. None of them uses delta. And we go into the literature and you see in motoring, usually they do the Y kind of connection, which we didn't use, but it turns out that is the thing. There are 3 different laminations that were used, X type, Y type and Z type. All of them have Y type, all of them. So it must be that this is, if you do this, you have an optimal property. We allowed 16 gauges, gauge number 1 to gauge number 16. As the gauge increases, you get I think it gets thicker and thicker, right? These wiring that you see, diameter gets bigger and bigger. All of them had gauge number 16. All of them, gauge number 16, all of them. There must be a reason why this is so. So that's the thing I'm talking about, the being constant, right? All those other 15 of them could have come. And if you change any of them to one of the other 15, you will be here in this gray region, which is you are not Pareto optimal. When I'm maximizing this and minimizing this, this is my objective space. So here is my Pareto set. So if you're non-optimal, you will be in this set on this gray region, right? So how are these solutions changing? With this one, sorry, not even this one. 18 turns. So I should have the 5th one. Okay, let me finish the thought. So we allowed so many turns. So this wiring is turned in the Z or Y or whatever we are using, right? So we allowed 10 to 80 turns to be there, any integer. All of them has 18 turn, fixed 18 turns. So once you learn this, that this is the way to do optimally design, you can now get these innovative ideas that, oh, I can now have a turning machine which will do exactly 18. Because if it's a universal turning machine, you have to go and set up the number of turns you're going to do, and there may be 1 or 2 error you can get. But this tells you, if you want to optimally design this, you have to have 18 turns only, right? So you can now, it can give you some innovative ideas that let's go and design a turning machine only with 18 turns, not one less, not one more, right? So how are these things changing? It's changing with the number of laminations. So I actually had number of laminations is another. So there are five variables which I thought were what we were using. So number of laminations do not get fixed anywhere. But if I see what is the number of lamination here, it is this much. It's about 18 or 19 or maybe 16. When I'm here, it's about 175 or something, right? And you see the number of lamination is linearly increasing as we want more and more torque. So now I get a recipe of how the motor will look like when I kept the other 45 variables fixed. If I change them, there will be a different configuration. But with those being fixed, if you want a larger torque motor, you will have an elongated motor because you are adding more and more laminates. That's what he said. That's the recipe, that keep all the other things fixed, 4 variables fixed, only vary the number of laminates. That's how you go from this Pareto points to that Pareto point. You see how much information useful this is to a designer? Next time He's doing this, he already knows a lot of stuff about this. So not only that I'm giving them the solutions, but also I'm giving them some rules, some thumb rules, some design rules, design principles. So that's the byproduct that you get when you are doing multi-objective optimization. I'll show you a few examples now. This is a cantilever plate design. There are a lot more elements we have here. This side is fixed and I'm applying a load over here, and this is an open area. It's more like a topology optimization. And our goal is to come up with a topology which is going to do two things: minimize the weight of the structure, simultaneously minimize the displacement anywhere. So it turns out there's going to be conflict. If you have a very lightweight design, it's going to deflect quite a bit, right? And if you do a very good, almost zero displacement, then it's going to be heavy. So we want to find all of these and then see what properties are common in them, what are invariant in this design. So first we go and find 1, 2, 3, 4, 5, 6, 7, 8 different Pareto solutions. You see, having a very low weight and very high deflection, and a low deflection and large weight. Okay, so once we get that, now we want to see each of them, and here are the solutions. So these are the 8 solutions. This is the minimum weight, this is the minimum displacement. So now you can observe what's happening. First thing you notice that I applied the load here and this side is fixed, so there is a midline symmetry I can expect. Okay, and all of them have this midline symmetry, which is not told. You see, they are slightly different from the top to the bottom. You see, this part is there, this part slightly different, but more or less symmetric. Okay, so that's one common property, that if you have a symmetric load, your design is also going to be symmetric. Then we have a lot of more innovation. If you observe this, simple way to do this is connect from the two ends to where the load is. Okay, and you need an adequate thickness so that it doesn't break because of the load given, right? Next innovation that come is what you call as a stiffener, right? Yeah, joint support, and then we get the stiffener, which means these two are long elements. If you join this with some elements, then basically your cantilever effect comes only for the small region. You can reduce your dimension there. So this is an invention. Of course, this is a simple one, we all understand it, but this one tells us how the trade-off between weight and deflection, what kind of innovative properties that can bring in. First is a simple one, connect with long arms. Second one is try to reduce the long arm with the idea of stiffener. And then the next trade-off was, okay, get back to the same design but with thicker arms. So this, as you go this way, you're getting heavier and heavier, but you are also gaining in the displacement. You're not having too much deflection. Then this one is rediscovered again as a trade-off, and now the stiffener gets thicken, eventually the whole plate. This is what we usually call as the chamfering, right? We do this because of various reasons, but one of the technical reasons we do chamfering, which maybe many of you may not know, is that these elements here at the corner do not contribute to the stiffness much, but they unnecessarily makes it heavy. So stiffener, this chamfering is usually done so that you don't have a sharp corner. But there is another reason in this case, is that they are useless in terms of stiffness, right? So the algorithm finds it. You see, again, it's not entirely symmetric, but it finds that if you eliminate this, you are not sacrificing on stiffness much at all. Okay, so these kinds of methodologies have a lot of interesting innovations to observe. So if I would say you are working in a company where you are doing one kind of optimization again and again, but different dimensions, different sources, different values of weights or things like that, I think one point you should ask your boss that I need a month to understand this problem. Don't give me any other thing. I'm going to sit and study what is this property of this problem, and this could be one thing you should do. Think of 2 criteria at least, come up with Pareto sets, and then see what are the properties, how things are changing. At the end of that, you give a report to your boss, you will be very happy. In fact, some companies, I know Siemens, some people are here, but Siemens US, once a year they allow 1 week only for all their employees. They stagger it, of course, free. You don't have to do anything regular work that you're doing. You can do anything you feel like, but you have to work. But whatever you had in mind, do it at that week. And I found that some of the people I'm working with, that 2-3 weeks before that, they get very busy talking to me that their free week coming up and they want to do something with my help, and whether I'm available that week, and they sometimes come over, we have Zoom meetings with that. I think that's a good thing companies should have. Give, at least their research guys, give some time off to just think wild and relate it to your problem, but think wild and do some of these kind of studies to understand what you are regularly doing, because you may be getting swamped with things and you don't have time to think, right? But sometimes you need that. And this could be one way you can really understand once and for all what is your problem. I'll show you something which you will find interesting. This was my student Fayaz Ahmed, who is now a faculty in MIT. He was here for the NCM DAO conference in 2 weeks ago. What he did this as a class project of my optimization class. He looked into this innovization. He thought, we can use this idea to come up with a team for playing anything. So he took the T20 2020, right, part of the cricket game, and he looked at the Wisden's record of every player. There is a record, right? How much is their batting score? If there's a bowler, how many wickets he has taken, and all these statistics are there, at how many runs he has given. So he's actually, this is done in 2010, okay, before the 2020 cricket. No, I think that was over, and then he finished the task after that. So every dot here you see is a team of 11 players picked up from this Wisden. There are 129 players he picked. Out of that, he's picking 11. So it's a huge search space. And he's following all the 2020 or T20 as you call it, I think, rules. Like there cannot be more than 4 foreign players. There has to be at least 1 bowler, 1 wicket keeper, and all that stuff is there. And then he has a 11 player team. And then there is another team with 11 players. So now you are playing against many. So he is actually handpick few good teams, and every team is playing against that, and he's got a score. So how much batting score that team is going to make, that is on this side, and we want to maximize. So he put a minus sign to minimize that, minus of batting score. And then he also have that team's bowling average, how much run on an average they would give. So these are all simulation, not real life playing, right? So with that, he got 2 fitness and he builds it, and if any team doesn't have a wicket keeper or something, he's going to reject it. Those are constraints. At the end, he's used NSGA2 and he got this Pareto set. Okay. Now you see that there are lots of good solutions. How do I say this is good? I asked him, let's take that year's winner, and it was Chennai Super Kings, by the way. And we take all the players from there and get their statistics and put them, what was the bowling and what was the batting, they come here. So I could give you from his set lots of teams which would have played better than Chennai Super King on the simulation. Okay, but there are a lot of other things like 2 players chemistry being in the same team. All these we don't have here, right? But this, to say that these are, if all these were here, I would have said no, there's something wrong, right? When it's here, it means that okay, I've got some good properties of this string which is better than the champion of that year. Okay, so that's the first thing to do the optimization. Now that I have 11 players in each of them, I can actually make a frequency distribution. Take a particular player from here or every player from here and see how many times he is appearing in the other teams. Next player, how many times they are appearing. Here is the plot. Only 29 of 129 is participating in this. All other 100 is never picked in any of these Pareto teams. Which means if I am the owner, like Shah Rukh Khan or someone, that I want to build a team or for next season, I can do this study and look at all these guys. You may recognize some of these people way back 2010. They are not playing anymore, I think. They were the good ones, right? And you see that Saha, for example, comes more than 90 times out of 100 teams. So he's a prized player, right? Similarly, there are other. So if I am the team owner, I'll probably pick some of them first. And you know, in this T20, they release a bit of money first, and he said you can pick any number of players, but you cannot spend more than this much, so that all teams are almost equal. And then once you spend that money, another level of money is put, and then you can again buy another. So you can get just one player with that money or 5 players with that money. So you can play that game, and in fact in the paper he did all that. We got very good reviews on that, particularly from UK and South Africa. There are some, because these are the cricket playing nations. I told him to go and look for if any of these team owners are going to be interested in the software. But I think it did a bit, but nobody was interested at that point, because it's only few teams and they don't believe in these kind of things. I don't know whether you have seen Moneyball. There is a movie with the baseball in US. They actually did something like this. It's a not so good team from California, and this manager or the captain, or sorry, the coach, he hired someone who did a lot of stats against every team. What could be the strategy? Although the team being not good, they actually went all the way. So, and there is a movie made about it. So that's kind of similar what we are talking about, coming from the two functionalities of a game, looking at the trade-off, and then figuring out not only the good teams that you can get out of it. So next time I do this, I'll probably concentrate somewhere here in these teams and see who are the players there, because they really make a good compromise between the two, right? But then this is an extra study which we call innovization you could do to pick your team. Okay, I think I need to show this one too. This is exploring design spaces. So this was done by a PhD student from ETH Zurich, and his supervisor is Lothar Thiele, with whom I'm collaborated, and I was the examiner of her thesis, so it was a very nice thing. This was one of the examples she took. Basically exploring the design space. So let's say I am interested in a bridge design over a river. Only one goal is weight minimization, okay, weight of the bridge or cost of the bridge, okay. After she ran evolutionary methods on this is the population. You see all of them look the same, right, almost the same. So you get a general, this is the best one in terms of weight. So you can see that there is a general understanding, agreement that this is how the design is going to be. Great, there is not much you can learn from one design. What she did next, he said, okay, I'm going to do a bi-objective where weight is one to be minimized. Second objective I'm throwing in, that's going to say how different a solution is with respect to this minimum weight design. So she defined a distance measure between any of these, one from here and one from here, and that one you want to maximize. So you want to get away from this minimum weight design as one of the objectives. You don't want to see this again, okay? And you also want to minimize. So there is a pressure for the algorithm to go towards it, but the other objective says, no, don't go towards it. So what will happen? You'll get a Pareto set where some of these solutions may stay, but you also have other diverse solutions, and this is what you get as the end of the run. You see lots of innovations here. This one is particularly interesting. There are many others. See, there are two of them coming like this. You know, this is another interesting one. This is another completely interesting. A lot of railways do that. They don't want to have anything on top. They do like this. So yeah, I mean, it's a simple two-dimensional truss they have done. But you can think of when you are sitting down on finalizing a design, you just throw in another objective. Sometimes we call this kind of stuff is multi-objectivization, which I actually wrote on the board the other day, objectivization. Because the problem is not multi-objective. Your still goal is to have single objective minimization, but throwing in another objective gives you a lot of new ideas. And then you can decide which one you want to do, whether it's this one, or one of this one, or anything that you could do. So we use this, Deepak, my student, did a lot of MEMS design in his thesis. These are small weight, you see, only 0.7 grams kind of thing. The thing I want to tell you is that when you do a single objective minimization of the MEMS structure with all the constraints, minimizing the weight, he got a 0.7 gram solution. This is the single objective minimal solution. When he threw in another objective very much like this, diversity of the structure, difference from that solution, he gets these points as Pareto. You see these Pareto solutions? The important thing here is he's got 3-4 solutions here that have smaller mass. Even one is quite less than 0.7 gram, which he could not get using the single objective minimization. So what is wrong here? Because this solution also existed in his single objective run, he just simply didn't get that. So his optimization was not perfect when he did that, because you are using an algorithm to a complex problem. You got stuck somewhere. Why you got stuck? Because there is not much diversity left in this complex design. Sometimes by crossover mutation you get a very good design, and then to improve this to a new one you need another good design, and sometimes you may not get to that so easily, and so you're stuck for a long time. And in complex design these things happens. But if you have a second objective which is contradictory to your main objective, by force the algorithm is trying to maintain diversity, so your population will never become similar. And now your crossover operator works very nicely, because you have differences in solutions. When you cross, it can invent something new, and that's what has happened here. We're not sure if this is the best one, but at least it gave a much better results for that objective than the single objective. Yeah.
Can this problem be solved by increasing the population?
Yes, you can increase the population size to a point that you get towards this. Yes, you can overcome some of these. You can try with other hyperparameter tuning, and maybe you can do that. Yeah, but here his goal was just run it an algorithm many times, and this is the best he got. And then he's done the same population size, same number of evaluations, but with a bi-objective. Okay, so I'm showing you here some few features and advantages of multi-objective optimization. Yeah.
Yes, sir. For both the cases, the design domain is same.
Design domain is the same. Yeah, it's that same variables represents the entire design space. There is nothing else. Here also is the same thing. It's just that in the optimization, I told you in the beginning, there exists no algorithm that guarantees you the optima if it's an arbitrary problem. More complex the problem is, more you deviate from the optima, because you can get stuck in many different ways. I can have a constraint boundary which is so nonlinear, you are improving, come and got stuck into the constraint boundary. Now you need a big jump to go to the other side, and your algorithm is not able to do, because it has certain ways it creates new solution. It's always end up in the infeasible place. And that's where you could do hyperparameter tuning. You say, I'm going to increase my mutation probability. Maybe you can jump. So all these adaptive algorithms you may have to use to overcome these, even then it's not guaranteed how many times you can be so successful and avoiding some of these. But this is another way that keep everything design domain, search space, everything the same, just add another objective. Because we know that adding another objective introduces diversity. That objective better be in conflict with the main one that you are trying to do. So once you have that, you're going to have diversity, and then you don't have to change any other thing, because your population is now always diverse, and then your crossover really works well. Mutation, it doesn't matter, but crossover works well, and then it can give you some new and interesting designs. Okay. All right. Yeah, I'm going to do one or two more things very quickly. Question, yeah.
Multi-optimization, like how do you know that this many evolutions they have to go to reach optimal value? How do you know that this many evolutions?
No way of knowing. In any arbitrary problem, there is no way of knowing. So we have some termination conditions which says, do I have a target? Most problems from industry when I get, they have an existing design, existing solution. Like the one I showed you yesterday at the end, 184 kilo is their best design. And they look at their competitors, they are having about 175 or so, about 10 kilo less, and they are wondering why are we not getting to that level. So they try, they couldn't, then they see, okay, who is an expert in optimization? Let me pose that as a problem to them. My goal is, can you reduce the weight by 10 kilos and satisfy all of these 146 constraints and all that? So then our goal is, as soon as we get something better than 174 or 174 or better, we stop. We don't have to continue to run to the optima, because some people said they are interested only in finding a feasible solution, not the optimal solutions. Oftentimes that's the case, okay? But if you're doing it for the first time, right, no existing solution is there, so you don't know how to compare. But you have all the time with you to really try, then keep running. You can also observe what's happening. So the objective function, if you're minimizing, you will see it's dropping, and what we call as a punctuated equilibria, it stays for a while because no other better solution has been found, and then at some generation it improves a little bit, and then it stays for a longer, and then again improves. Now you can, actually it's a dynamical system, right? You can understand with this kind of time that you're spending on each level where you're getting stuck to predict when you are expecting the next jump, okay? You could do that, and some theoreticians are doing that once you understand that dynamical process. So you have to wait that long, because not, why is that you have to wait? I guess mentioned you a little bit. So let's say you have a objective, right, take a simple problem. Okay, so you are starting from here, okay, pretty quickly. So this is your function value, this is your f(x), and this is, let's say, your x. So you can drop very easily, quickly, but when you come here, you are at this stage. Only if you are here, you will have an improvement in the function value. When you are here, only if you are here, you have an improvement in the function. So as you are approaching the minima, the region from which you get better solution also reduces. And this reduction, in this case not, but in many complex problems, exponentially reduces these region. Like the billion variable one I showed you, there it just reduces very, very fast. So once you are 99.6, to go from there to 99.5, you have to wait a lot, because not many solutions is going to give you this little improvement. But if you are at 70 to, let's say, 70.1, oh, very easily you can get one, because there are many, many ways. You see, when you are here, all you have to do is you should be anywhere here, and then you have an improvement in the f, right? So that's the reason why, as you approach the minima, you have very few better solutions available in the search space. Unless you are organized with your search, it's difficult to get to that, and then you are stuck for a long time. So there are ways to terminate from previous stuck situations and see how long it will take, and you say, I don't have that much time. Oftentimes these are, I mean, yesterday we were talking to one of the ex-students from here. He says time is the main thing. When you're solving industry problems, they usually don't care whether you've got the optima or not. They said, I'll give you 10 minutes, and what can you give me? So then you have no issues, like you run 10 minutes and whatever is the best you declare, and then you see, is it good or not, okay? And then you come back and say, maybe I could have done something better. In 10 minutes you go and change it. So oftentimes it's the time target or the number of evaluations that becomes your target. Okay, but it's a good question. Any other question like that or anything? Okay, I'm going to talk next about the uncertainty handling. So imagine this is my objective function. This is, of course, the global maxima, if I'm maximizing, right? You see the highest value. So as a designer, I would be interested in knowing that. But if I cannot, I give you this solution x, right? Whatever is this x, I give you. Say some value, let's say 10. And now you try to implement in a machine which has some tolerance. So you cannot guarantee 10. Let's say it comes like this with a distribution. When I actually implement, I cannot adhere to the exact value. Now for some of these values you are really bad. Although if you could achieve this exact value, you are very good. And I already showed you one such problem, the solar optimization with Spain that I've done. We had these kind of peaky functions, right? Isolated optima. So nobody likes in practice this kind of optima because they are not sure of adhering to this. Rather, if you choose this solution and you have this kind of uncertainty, you are from here to there. So they are not too different from each other in terms of function value. So you have some stability there. So these are called robust solution. And so although this is the best, your goal of optimization is to find this, not that. So how will you find the second best? It's very difficult if you want to be in your class the second topper, not the topper. It's much more difficult, right? Because you have to make sure you are getting less marks than the topper and higher than the others. It's much more difficult. So what we come up with here is that we average with the tolerances, we average out. So it's a running average we do, and this dash line may have come up, and then we optimize the dash line. And that way, this one may not have gone down much, but this one will gone down because of the averaging, and this becomes the global optima. So instead of minimizing the solid function, you minimize the dash function. Okay, so this is one of the approaches we do. There are different kinds of uncertainties, and because of time, I'm not going into that. In multi-objective, you have F1, F2, you have a Pareto set, goes from here to there. You can look into every solution here, go to the decision variable space with a small ball around it. That means you perturb these points and you see where the function values are in the neighborhood. If they are not changing much, means it's a robust solution. If the solutions change like this here, when I go to the same ball and there is a big fluctuation in the F values, which means this is sensitive. So which means this is not a robust solution. So in multi-objective, if you want to find a robust front rather than a Pareto front, it may be another one here. So you should find this rather than that. So you don't find the Pareto front, we find the robust front, and the robust definition you have to provide, which we have a couple of ways to do, and then we can find the respective fronts because we have now defined what we mean by the robust front. Another version of this, when you have constraints, is called reliability based optimization, where if you take the deterministic optima without the uncertainty that the variables can come, you will usually get a solution that is at the intersection of more than one constraint, and that is usually very, very sensitive, because if you have fluctuation like this on the variables, you can be infeasible most of the time. Now you say, okay, I don't want to be at the brink of being feasible and infeasible, I want to go inside so that I get a reliability that 99% of the time I want to be feasible when I get this, maybe 1% of the time I am here and I am infeasible. So you specify a reliability, and based on that reliability you will move inside the feasible space. How much depends on the reliability. So once you set up the reliability, you get into a problem like this, which are called the chance constraint problem, and then you solve that problem and you get this. But you need to specify the reliability. That's also not easy to set, but you could do some preliminary study to figure out what reliability you should set. Okay, I'm not going into the details of this. Also, I'm going to skip this one just by saying that many problems in practice, it takes time to evaluate every objective function. Like if you're calling a finite element code or a CFD solver, these things take time. As I said, I have done some problem where each evaluation takes 2 days. We've also done some such problem. Now when you have multi-objective, so there are several objectives to be evaluated. Each of them is taking time, constraints to be evaluated. So am I going to make a surrogate model for each one of these objective function and constraints? Or am I going to combine all the objectives into one, like a weighted sum or maybe some other ASF or something, and then I surrogate model that. So one time we sat and then we came up with this taxonomy where we have 10 different methodologies. First one, M1, is where everything is meta-modeled independently. All the objectives and all the constraints are meta-modeled independently. And then there can be 2 versions of this. I can use one by one to find the Pareto set using point-based methods, or NSGA kind of method or EMO method to find multiple of them. So we call this M11 and M12. Then there is M2, where I keep all the objectives independently modeled, but I combine all the constraint like a constraint violation for every solution, and I meta-model this function, not the every G function. Okay, so I've got one combined function. So it's, if there are M of them, there are J of them. This one I have to do M plus J meta models. Here I have to do M plus 1, M objectives and 1 constraint. Again, there are 2 ways to solve that. M3, I combine this into one, okay, and keep all the constraints independent. So here I have 1 plus j. Again, there are two ways, and M4 there is 1 and 1. I have just two models, one combined objective function, one combined constraint function. Of course, when I do one combined, I have to run this multiple times because I have to change the parameter so that I can generate my Pareto set. These two are interesting where I have combined the objective and constraint together, okay, and I could do one by one, that's I call M5, or we could find all of them simultaneously. So this is the most smart, intellectually most telling kind of method, M6, and we spend a lot of time developing algorithms for M6. There are several comparisons that comes, and you see some cases M5 does better, some cases M6 does better. So this told us that maybe we should adaptively decide from start to finish which of these 10 methods we should use at what point of time. And we get very good results, you see, with very few evaluations. These problems otherwise takes about 10,000 evaluations to get to this performance, but when you do with these surrogates, you are actually doing it very, very quickly with only 800 evaluations. There are ZDT functions with just 500 evaluations. Okay, I'm going to skip all of that. Yeah, this is the adaptive method where you see now any one of these ZDT1, for example, all the 10 methods are here. It says first few generations, okay, first you are concentrating between M11 to M2 to M11 to M22, and these are sometimes you are using, but after this point mostly these 4 methods that are needed. But if you go and take another method like ZDT6, for example, another test problem, we are hardly using M11 to M22. It was only those methods that are used, you see, and some of them are used more often, some of them are used less often. So it's automatically deciding based on the performance of each of these methods what to do. So I think these are very interesting ideas and can be very, very efficient in different problems because you are not specifying what method to use. The algorithm is finding it. Okay, 2 more topics very quickly. First is there is a lot of work now coming from machine learning literature trying to improve the performance of EMO. Okay, so we've got a book recently. I don't know. Yeah, the picture of that. So it just came out, and maybe we'll see if there is a copy can be purchased for the library, so you can have a look. One of the chapters from the book is, I'm showing you the results here, is that how machine learning can be used to improve. So let's say that these dots, can you see? Yeah, these circles are, let's say, my generation 10 points, and I did another 10 generations of NSGA2 or whatever, or this is NSGA3 actually, and I get these points. There are other points, but these are the best ones closest to my reference line. Remember the reference line we talked about? So these are close to my reference lines. Okay. Now what I do is each one of these points I associate with what has happened after 10 more generations have passed. So this is my input, this is my output, this is my input, this is my output, this is my input, this is my output. So I get these pairs of x vectors of input and output. Input is a point that was 10 generations ago, output is the x vector of a solution along the same line 10 generations later. And I train a machine learning model with this x, same number of neurons at both sides. I train it for all of them. Once it's properly trained, that basically has captured how you have moved in 10 generations from these open circle to the red circles. We don't have any such operator yet in GA. All we do is crossover and mutation, right? And there are sometimes we do 2 mutations or 3 mutations depending on different types of repair that we want to do. But this is a new idea that says, oh, I have a history of how I have come to this red place. Maybe I can try to learn how I have come to this one through a machine learning model. And then when I use this to create a new offspring, I can actually fit this as input, this new recombination and mutation way generated input to this machine is actually here I can supply that offspring, and this trained model should give me a solution close to these red points. So, because if it learnt it, it should give me that. So, I can bypass some of the computations by just learning this aspect. Once I've done that, I could again go another 10 generations and learn from here, and from there I create these pairs and I can learn another machine learning model. Okay, there are a lot of interesting stuff. So, these machine learning models from the before to the end I can save. And now what I ask my student is, can you take a random solution? Let's create a random solution, send it to the first learned training model, output send it to the second learned training model, output to the third learned training model, and he's able to show that you come like this, come close to the Pareto set. So, basically you have learned with several learning models what to do. Doing it in one step may be difficult, but if you're doing it in multiple steps, it's relatively easier to learn, and you can actually do that. So, now not only you have solved, you find the Pareto set, you also have captured the landscapes, okay, as you come from the random place all the way near the optimum space. Okay, very interesting ideas. And you can see the performances. This is the hypervolume I was showing you as a metric. We do higher the hypervolume means better. So, if we don't use this, the red line will be NSGA3's performance. Okay, at generation 30, for example, we will be here with hypervolume of 0.3, but if you use this kind of learning, you have increased it. See, every problem we have an increased performance. So, to get to the same accuracy, I would have taken only a fraction of the evaluations, but I can actually improve this much of hypervolume by using this. And this is coming almost free, no more function evaluations, it's just that little bit of time for training the machine learning models. If you have a very fast GPU system, we could actually do this parallelly as we are running. So, some of these kinds of ideas are creeping in optimization and particularly in EMO area to take help of the learning and helping the algorithm. Every chapter here we talk about one such innovations. Okay. Another one from the book I'm going to show you, this is also interesting very quickly. Let's say we've done an optimization using either the previous one or just simple NSGA2, NSGA3, and we get some points like this on my Pareto set, okay, and I see that there are some gap apparently. Okay, my algorithm could, I showed you an NSGA2 run and I showed you there is a little gap, right, 2 places, and I said if you keep running it's going to get filled. I don't want to run. Running means more function evaluations, more time. So, I said I stop there. I use now all of them as my training set. So, for that I need an input and an output. What is my input? The pseudo weight. Now you know pseudo weight, right? Okay, pseudo weight. So, for each of them I can compute a pseudo weight, and that goes as my input to the machine learning model, and output is the corresponding x vector. So, there is a pseudo weight and there is a x vector. This is of dimension m, number of objectives, this is of dimension n, number of design variables. So, usually number of design variables are more than number of objectives. So, you will have a neural net that kind of expands like that, but I have unique pseudo weight for each of these x vector. I can train this, and what I will get is, if I give a pseudo weight, it should supposed to give me an x vector, which will, when I compute now f1, f2, it should fall right there. So, if I have very small error, I can reproduce that. Now, I go and see if I have to get this point, what will be the corresponding pseudo weight. So, I have a f1, f2 at that point, oops, I can compute pseudo weight from the formula I gave you. So, that pseudo weight I input to this, and this machine learning should give me a corresponding x vector. Okay, and now I evaluate f1, f2, and I see if this lies here or where, is it feasible, is it infeasible. That way I can explain if these points I do here always produces an infeasible x, some constraints gets not satisfied, I know why I haven't got any point there, because there is no feasible point there. Or maybe it's feasible, but it gets dominated by one Pareto solution, and that's the reason there is no non-dominated solution there. So, I can explain. Or the third situation could be that my algorithm just could not find it, but there exists and I find now a new solution. Again, that comes with just one function evaluations from this predicted x vector when you compute f's. There is no extra function evaluations you are doing, right? And I'll show you some examples now. here is the problem with this ZDT3. There is not supposed to be any point here, right? But I take these blue points and train my neural net, and I am now giving lots of points pseudo weight here, and they produce these points, which are all gets dominated by that. They produce all of these points, which it gets. So these are predicted by a neural net, but this is dominating it, saying, oh, there is actually a gap here. Okay. Another problem in 3 dimensions. All these red ones, I did not have any point. These blue points is what we found using NSGA3. I train them and I give pseudo weight so that the points come here. They all turned out to be dominated. This problem, all this blue I feed and I give pseudo weight here because there was no point found here. They turned out they are invisible. I got an X vector from my neural net, but when I evaluate the G's, they are invisible. And now I can explain to my industry partner saying, hey, we don't have any point here because they are invisible, or we don't have any point here because the function values there are bad. They get dominated by the blue points that I've already given you, right? So again, it's explainable AI, explainable kind of task that we are doing here. I'm not saying this is AI, but I'm explaining why I'm getting these kinds of results, right? You can also use this to fill up. Here is a problem where I deliberately took out some of these points from here and only use these blue points to train, and then I give some pseudo weight from here and see it reproduces points. These are feasible and it belongs there, which means my algorithm could not find these points. Okay, so these are interesting studies. EMO can also be used to improve the performance of machine learning methods. We do NSGA2 applied to these neural architecture search problem, NIS, where we are finding the neural architecture for doing some image recognition problem. And then you see all these are our points. So we are trying to maximize accuracy. This is like multi-objectivization. Usually you try to maximize this or minimize the error, right? But I throw in another objective, which is how big is your architecture, number of connecting weights. So we try to minimize this and maximize accuracy. We get this Pareto set. So there are 5 solutions here. This beats the Facebook's ResNet. Where is ResNet? Somewhere here. And then Google's AmoebaNet, which if you're in the field, you're familiar. You see, we can give you better weight, better accuracy with less number of, less size architecture. So there is a lot of things here that we could also use EMO to go and take some machine learning algorithms and try to improve. We also did a lot of transfer learning stuff with this EMO concept. Okay, let me not get into that. Couple of things that we are doing recently. I told you that some new ideas I'm going to tell you. These are our recent work with my PhD students. We're doing a couple of them I'm going to show you before I stop. So first one is what we call as regularized front. So let's take this example here. I don't know why. Okay, maybe you can see that behind. I should have had this later. Let's say it's a hypothetical problem I'm showing. Let's say I've got a hypothetical problem here, and I do a Pareto optimization with 2 conflicting objectives, and I get a Pareto set, which are these blue lines, right? Here is my Z. So you're familiar by now with all that. If I look at each of these blue points, I see the solutions. Okay? As a designer, it's too complex for me to remember that when I am, let's say this could be cost or something, or some performance. If I am improving or rather worsening in my F1, I see the solutions are changing, but very abruptly. A lot of features are changing. There can be still some innovation like regularity, regular polygon being the cross section and all these, but this is not enough for me. It's still too much for me to remember, right? I have to probably have a table lookup. If I want to look at this, then what is it? If I look to this, I don't see much similarity, but or maybe there is some similarity, but I cannot remember it, right? So now I am asking this question. These Pareto solutions are fine, but not always people in practice like optimal solutions because of these things, okay? They say, no, I want to see more regularity. So I want to see maybe solutions that look like this. Similar cross sections, it's just the dimension is changing. Then it's very easy for me to remember what's happening if I have to have a new solution in between what to do. I probably take an interpolation between the two. There is no other thing changing and all that. So I want a very simple, regular looking set of solutions. Okay. I can specify this by saying cross section should be the same. I'm not saying whether it's circular. I'm not saying how you should change this, but I'm saying I want to see a similar cross section. Cross section is not changing over the line. So that is my regularity. Now I need an algorithm that should not go and give my solution here, far away from the original Pareto set, but very close to it and having this kind of property. What property? Whether it's circular, whether it's triangular or something, that algorithm has to decide. So very simple keywords I'm going to give that I like. Now the algorithm should go and give me a regularized front, is what I call, which is not far away from the original Pareto set, because I still want to keep these two important things. Okay, not far away, not like this, also have this kind of property. So we came up with algorithms, and you can see this is B and H problem. The blue one is the original Pareto set, and we find the red one. Let me see if I have the, yeah, now it gets below this. So what happens is that now it's the, okay, one more time. Okay, let me just tell you that what happening is that these blue points are going like this. What happens is that the blue ones will go like this and get stuck here at the upper bound. And this could be too complex, although it's a Pareto set, for me to see where is the cutoff and all that. The red ones go like this. It's very simple linear relationship. From this point to that point, this x1 versus x2 has this linear relation. If you increase x1, x2 will increase in a linear fashion. Very easy for me to remember if you tell me the slope, the equation of the line, right? And now I got a Pareto front which is seen, not much compromise. From the blue, almost the same f1, f2 information, but I have a much better regularized front. So these are all practical stuff, thinking of how, what they may like or not. So that is one of the thing. The other thing we are doing is called innovation path. Let me now again, okay, maybe you can see that. You all use the QWERTY keyboard, right? In all these are QWERTY keyboards. This is the QWERTY keyboard. So I asked my student that take a novel with lots of words and type using the QWERTY keyboard. Usually you have your fingers put initially and then you move your finger to type, right? He's counting as he's typing the whole novel how many finger movement is taking place with the QWERTY keyboard. And do I have those numbers here? I don't, but yeah, you can see here. It's about 180,000 finger movements. So you type maybe few pages and your fingers will get tired because so much movement you made. Is it the problem with the text or is it the problem with the keyboard? These keyboards are designed many years ago when typewriters used to be, right? And they would put this keys in a way that two frequently appearing keys, one after the other, are put away so that there is no jamming, right? Because these are mechanical typewriters. You press one, it takes a bit of time the key to come up, and in the meantime, if you've typed the other one, there may be jamming, and oftentimes typewriters used to get jammed. Right now, we don't have that issue. There is little spring in every one of them, right? It's not an issue. Why are we still following the QWERTY keyboard? Because right from our childhood, we got used to with this, right? So I told him, take that novel and optimize a keyboard configuration. He came up with this. Would you ever use it? By looking at it, it's ugly, right? There is some semicolon came there and things like that, right? But if I force you right from your childhood, you'll probably get used to it, right? I have to force so many people to get it used. So this is a situation which happens in many industries I've heard. They say, here is an assembly line, we are stuck with it. Because changing it requires a lot of money, a lot of time, shutting down. I cannot do that. My boss is not going to allow me. But I really wish there was a bigger place here for keeping all these before the slow machine, you know, to stock all of them. But I don't have enough place. So I'm sending it somewhere else, and it's a lot of time is getting wasted and all that. So you wish there was a change in the design for the new objectives that you have, which was not the case when it was first developed. Very similar situation. So you are reluctant to go to this one, although you know this is a better one, good for your finger, but you don't have this because this change requires time. So we say, okay, can we find some intermediate keyboards going to the final one, where we say how many changes we can allow maximum, so that it's adaptable with given little bit of time. Again, it's adaptable. So we may want to do this in 3 years time. Everybody from now on for next 1 year uses this keyboard, and then next year they're going to use this keyboard, next year they're going to use keyboard. May not be for the keyboard, but at least for the industry problems we can achieve that. Temporarily add something, remove something, so that eventually we're going towards that goal. So which means this is my current design in terms of the original objective, which is faring not so good. I want to go to a much better design. Maybe this was 70,000, less than half of the finger movement to type the same thing with this. But then that's different. It's about 12 keys different from here to this. I cannot ask 12 key difference to be learned by people so easily, but one can maybe easily adapt to that one. So we have 2 more intermediate. If you want, I can do 1 keyboard, then I can have maybe many of them here. So slowly you move there. I can have that as a parameter, and then I can have a transition. So this is what we call as innovation path. It's very useful for the design. I think for the department, the ED department here, we're talking about design, is design transformation, right? Design changes. And we found that this is called, in Japanese, it's called Kaizen principle. They have already talked about it many years ago, that small gradual changes to a big change in the design, if you want to do, is acceptable by people. The other is known as kaikaku. Okay, that one means one big change, and that's usually not acceptable because it costs a lot of money or time or things like that. So we are basically talking about finding number of intermediate solutions we call innovation path towards our target. Does it tell you something about multi-objective optimization? What if I can think of these 2 as objectives and minimize? This looks like a Pareto front. So I can actually formulate a multi-objective problem, solve it, and the results are going to be my intermediate points. So they are not Pareto designs. These are some artificial objectives we have created so that I can find these Pareto solutions, which is my intermediate solutions to this. So we are applying these in many. Last August, I gave a talk in Mahindra University here in Hyderabad, where we talked about these. 2 groups of students got very much interested. One we are doing with music creation, so there is a lot of people are depressed, and music therapy is one way you can uplift them. So they are at a stage where they like sad things, but they should be liking joyful things. And in one step, if you do, it disturbs them even more. There are all these psychological records. But if you slowly move from there with 1 month, 2 months of new music, it's not too different from what they're used to, but there is some joyfulness. And then another, you can recover them. Of course, we haven't gone to that stage yet, but that's our goal. We're in the process of finding these different music compositions. And another one is dealing with a city bus network. Suddenly you cannot change to a completely different route and bus, but we are slowly changing it, keeping in mind the existing ones. So I think there is a lot of, this is another application of multi-objective optimization in design, slowly changing some designs. Okay, that's all. I will spend time here with you, but I enjoyed talking to you, interacting with you, and hopefully you got something out of it, starting with optimization background, little bit point-based, population-based, single objective, evolutionary methods, and then to multi-objective, the principles of multi-objective, like the Pareto concept, different types of definitions of domination. You can also define your own, like we have these generalized domination principles, and then some algorithms, and then we talked about different extensions like, for example, today, innovization concept to some of these new ideas. There are a whole lot of other stuff that are going on parallelly. Once this idea of finding Pareto set number of different solutions are there, you can use it to your benefit in many different ways. All you have to do is think about what are 2 or more conflicting goals for your problems that you want to choose. So you see the trade-off between them, and the solutions with those trade-offs are going to be interesting to you. Okay, so then you can employ these methods and go and find the solutions. The source codes are available, like the NSGA2 basic code and RGA I gave you, but I mentioned to you about PyMu. That is more professional looking software. It has a GUI kind of thing, right? No, it doesn't have GUI, but it has a lot of documentation and lots of test problems already there you can call to understand, and you can put your own functions. A lot of industries are using it. That's freely available, but also there are commercial softwares where you have support from the commercial vendors. Siemens is one, Estico is another from Italy. If you will be joining a company and think multi-criteria is the way to go, or you want to try to convince to get a copy of one of those and then see, or you yourself can try these public domain softwares. There are other public domain softwares. I mentioned ours is PyMu. Then there is JMetal, then there is PISA. These are the three mostly used. There are others that are Borg. These are all public domain.